Welcome to session 11, the penultimate session of the Digital Electronics Problem Solving course on ISSS. I'm your instructor Sachin Sampath from the Indian Institute of Science, PhD scholar. In this session, we'll do problems from chapter 6, which is based on registers and counters. There are a lot of questions in this chapter. Unfortunately, it's only a 24-hour course, so I won't be able to solve all the questions. There are 30 questions. I might be able to solve about half of them. Let's see if I can speed it up. Otherwise, I'll solve about half, and the rest you can try it yourself. Let's begin with problem 6.1. Okay, there are a few theoretical questions at the start. I'll skip the theoretical questions. You can read about it in the textbook yourself. You can look up theoretical answers online. They are not in the textbook itself. I'll start with question 6.4. Instead of writing down the question, I'll just say the question. Alright, there's not much time, only 2 hours to cover 30 problems. So I'll just read out the questions and write the question number. The questions can be found in the questions are from this textbook titled Digital Design with an Introduction to Verilog HDL, 5th edition by M. Morris Mano and Michael D. Siletti. It's a very popular textbook used by a lot of electrical engineers and communication engineers, electrical communication engineers, etc. Anybody who wants to study digital electronics might have come across this textbook. So all the problems are from that textbook, and for the sake of saving time, I won't write down the questions from here on out in both this session and the next one. Problem 6.4. The contents of a 4-bit register is initially 0110. So you have a 4-bit register. Okay, they aren't talking about any particular output here. The register is shifted 6 times to the right with the serial input being 10111100. So initially the register is storing 0110, and then serial input 101100 is fed into the register, shifted right 6 times. What is the content of the register after each shift? So initial contents are 0110. After the first shift, the LSB of the serial input 0 is shifted to the first MSB of the register, and each of the bits of the register is shifted one place to the right, and the LSB of the register is discarded. So 011 is shifted right, this 0 is discarded, and the LSB of the input 0 is shifted to the MSB of the register. In the second shift, 001 input is 0. Third shift, 000 input is 1. Fourth shift, 100 with input 1. Fifth shift, 110 with input 1, and in the sixth shift finally you have 111 with input 0. So after shifting 6 times, the contents of the register are 0, 111. Problem 6.5. The 4-bit universal shift register shown in figure 6.7 is enclosed within one IC component package. Draw a block diagram of the IC showing all inputs and outputs. Include 2 pins for the power supply. Draw a block diagram using 2 of these ICs to produce an 8-bit universal shift register. Okay, I'll skip that question. 6.6. Design a 4-bit shift register with parallel load using D flip-flops. There are two control inputs, shift and load. When shift is equal to 1, the content of the register is shifted by one position. New data are transferred into the register when load is equal to 1 and shift is equal to 0. If both control inputs are equal to 0, the content of the register does not change. So when shift is 1, even if load is 1 or 0, it doesn't matter. You have to shift by one place to the right. When shift is 0, if load is 1, then you have to load. If shift is 0 and load is also 0, contents of the register remain the same. So 4-bit shift register, so you need 4 flip-flops. Okay. Same clock pulse through each of them so that the shifting happens synchronously. Outputs are, this is the LSB O0, O1, O2, O3. There are two control signals, input, shift and load, and there is an input signal, so 3 signals. When shift and load are 0, 0, the output should remain the same. So if you have shift load shift complemented and complemented form of load. Do they specify anything about how the data is shifted? Okay, they have not specified anything. I'll just take it as shifting left. So for the first part, when shift and load are both 0, that is shift shift bar and load bar are 1, then you must get the previous state. Since these are D flip flops, you must give the previous state as the input to the D flip flop in such a condition. So you can AND it with the present state. I mean, and when shift load are 0 1, you have to transfer input to the register. So shift bar load. Using that, you have to transfer input. Okay, drawing all this is too cluttery, right? So I won't draw all that. I'll simply say shift is S, load is L. Shift complement is S bar, load complement is L bar. And then I have input serial serial input, which is I. Now what do I do? I take the OR of shift and load are 0 0, then I have to preserve the state, so it's S bar L bar O 0. If shift and load are 0 1, that is S bar L, then the input must be, you have to transfer some input to the register, so it's parallel inputs I0 I2 I1 I3. So for the first flip flop I'll give S bar L I0, and if shift is 1, I have to shift the serial input Si to the output of the first flip flop. Same thing will be done with each of the flip flops. Except that when you're shifting, and shift is 1, you're shifting serial input to the first register, and then you're shifting O0 to O1, so it should be SO0. Then you're shifting O1 to O2, so this should be SO1. Shifting O2 to O3, this should be SO2. And there you have it. A shift register with parallel load, parallel input, and two control shift and load. Problem 6.7. Draw the logic diagram of a 4-bit shift register with 4 D flip-flops and a 4:1 multiplexer and 4 4:1 multiplexers with mode selection inputs S1 and S0. The register operates according to the following function table. I'll draw the function table. S1 S0 is 0 0 0 1 1 0 1 1. Those are the controls. The register operation is as follows. When S1 S0 is 0 0, there should be no change. When S1 S0 is 1 0, complement the 4 outputs. When S1 S0 is 1 0, clear register to 0 synchronous with the clock, and when S1 S0 is 1 load parallel data. Okay, you have four 4:1 multiplexers. You're giving the same control to all of them, S1 S0. And S1 S0 is 0 0, there must be no change. So the first input should be O0, O1, O2, O3. And the output of the mux is fed as the input of the D flip flop. When S1 S0 is 0 1, you have to complement the four outputs, so you have to give O0 complement, O1 complement, O2 complement, and O3 complement. When S1 S0 is 1 0, you have to clear register to 0, so you have to give 0 as the input. Then in S1 S0 is 1 1, you have to load parallel data, so you have to load I0 parallel data, I1, I2, I3. All right. There's a slight change here. This is 1 0 and this is 0 1. So let me redo this again. Draw it neater. So for 0 0, no state change. So you have to give the present state as input. For 0 1, you have to clear, so you have to give 0. For 1 0, you have to complement, so you have to give the complement of the present state. And for 1 1, you have to give serial data, parallel data, sorry. That's all. That's problem 6.7. Problem 6.8. The serial adder of figure 6.6 uses two 4-bit registers. Register A holds the binary number 0101 and register B holds 0111. The carry flip-flop is initially reset to 0. List the binary values in register A and the carry flip-flop after each shift. So first you have to get figure 6.6. Figure 6.6 is as follows. JK clock clear. This is the sum. So here is the shift register, serial in, serial out. This is X. The other shift register with output Y. XY is the J input. Sum is X XOR Y XOR the output of the JK flip flop. K is the NOR of X and Y. The clock is the AND of clock signal and I'll just call it shift. So clock signal and shift control are both ANDed together and fed as the clock. Problem 6.a says that this flip flop stores the carry JK flip flop. So shift register will shift first. You'll these two hold 4-bit numbers 0101 and 0111. Then after one clock pulse, the values are shifted to the right. So the LSBs of A and B, which is 1 and 1, are given to X and Y. So X and Y is 1 and 1. Initially carry is reset to 0. So 1 XOR 1 XOR 1 is 1 XOR 1 XOR 0 is 0. So sum is 0 with a carry 1. And that carry 1 is stored in the JK flip flop. So when X and Y are 1 1, J is 1, K is 0. So next clock pulse, the output of the JK flip flop will be 1, which is the carry of the previous stage. So in this way, this will do addition serially. And the sum is stored into the shift register A. So we can write register A, register B, and then you have the sum and the carry. So initially, register A holds the binary number 0101, register B holds the binary number 0111. Let's say the serial input is I3, I2, I1, I0, and we have the shift number here. So this is initial, where the sum we are not bothered about the sum, but the carry is reset to 0. Now after one shift, x is equal to 1, y is equal to 1, so the sum is 0 with carry 1, sum is 0, carry is will be 1. So after the so the synchronization here is a bit different because okay, let me see. Let me write down the inputs xy also, and then the sum and carry. So initially what happens is the serial output, it's the output of the final flip-flop in the register. Output of the final flip-flop is 1 and 1, right? So there is already an output x and y. Carry has been set to 0 forcefully. So what happens is the sum output is currently at 0. So what's happening here is the clock pulse is the same for both the shift register and the JK flip-flop. So suppose I am shifting, the shift is on, initially carry has been set to 0, and the output of the register serial output is output of the, it will be 1 1, so the sum will be 0. Alright, sum is 0, the inputs JK are 1 and 1. Wait, inputs J is XY, which is 1, input K is, let me also write that down, JK. So before any clock pulse is given, XY is 1 1, so J is 1, K is 0, sum is at 0, carry has been set to 0. After the first clock pulse comes out, the sum is shifted to the register A. So there's a shift by 1 bit, and the sum which is 0 is shifted here, and the serial input is shifted to the first bit. Okay, at this stage x is 0, y is 1, so j is 0, k is still 0. The carry has been changed to 1, because in the previous state jk was 1 0, carry has changed to 1. Carry has changed to 1, x is 0, y is 1, so sum of x XOR y XOR c is 0. Sum is 0, carry is 1. In the next clock pulse, what will happen is the sum 0 is again shifted here. You get I1, I0, 0, 1. So x is 1, y is 1. That means j is 1, k is 0. Previously j and k were 0, 0. So the previous state was retained. So carry was 1. Now the sum is 1 with carry 1. Sum is 1. So in the third clock pulse, that 1 is shifted to the first register A. You will get 1 triple 0. And then I2, I1, I0, 0. X and y are 0, 0. So jk is 0, 1. So carry is set to 0. Sorry, carry depends on the previous jk value, which is 1, 0. So carry is set to 1. And since the carry is 1, xy is 0, 0, sum is 1. In the next clock pulse, that 1 is shifted to the register A. B now has the complete value of the serial input. X and y we don't care now because all the addition has already been done. The sum is 1, 1, 0, 0. So we don't care about this. Carry is now 0. We don't care about the sum. So there's a slight difference here. The carry out and the sum are different. The carry out that you have is the carry out from the previous stage. Okay. And the sum that you have is the sum in the current stage. So the carry out is delayed by 1 clock pulse. So when you are writing out the carry out in the current stage, when you're adding 1 and 1, the carry out is 1. So you have to take the delayed value of the carry, which is 1. Alright. That is problem 6.8. Next we'll see problem 6.9. Two ways for implementing a serial adder a plus b shown in section 6.2. It is necessary to modify the circuits to convert them to serial subtractors a minus b. Use circuit of figure 6.y show the changes needed to perform a plus 2's complement of b. Using the circuit of figure 6.6, show the changes needed by modifying table 6.2 from an adder to a subtractor circuit. Okay, I'll leave this question as homework. It will be a good exercise for you. It's a big question and it will take up a lot of time. So you already have the serial adder circuit. In section 6.2, they give you two ways for implementing a serial adder a plus b. So you just have to modify them to get a subtractor. Something like what we had done earlier in the combinational circuit where you added the 2's complement. So you complemented all the inputs and added 1 to that. This will be a good exercise for you. You can do that as homework. I'll go to 6.10. We'll go to problem 6.10. I'll read the question again. Design a serial 2's complementer with a shift register and a flip-flop. The binary number is shifted out from one side and its 2's complement shifted into the other side of the shift register. Okay, that is the question. So you want to perform 2's complement. For 2 to perform 2's complement, you can complement each of the bits and add 1. That is the 2's complement. So initially we can set the output of the flip-flop to 0 using a asynchronous reset button. Let me draw you the circuit of the adder and then explain complementer and then explain the working of the complementer. This is a serial out, is a serial in, shift register, and the flip flop uses the same clock. We use a D flip flop with an asynchronous clear, so that initially we can clear the output to 0. So when you complement, the 2's complement of a number is nothing but the addition of 1 to the complement of the number, 1's complement of the number. So suppose you have the number 1001. Complement is 0110, and you add a 1 to that, you get 0111. Suppose you have the number 0110, complement that, you get 1001. You add a 1 to that, you get 1010. So in both cases, you can notice that the least significant bit is the same in the 2's complement form of the number. So initially Q is 0. We will clear Q to 0. The serial out is at the initial stage, the LSB. The LSB XORed with 0 is nothing but the LSB itself. So the initial output is the LSB itself, which is exactly what we want. Suppose we have the number 0110 in the register. This is the LSB and this is the MSB. The LSB is 0, so before any clock pulse is given, Q is cleared to 0. So the output, if this is our output, that will be equal to 0 XOR 0, which is 0. And the input to the D flip flop will be sorry Input to the D flip flop will be the OR of the LSB and 0, which is nothing but the LSB itself. So initially LSB is 0. So let's call this C, the output. C is equal to 0 and D is equal to 0. Q is equal to 0. After the first clock pulse, the value at C is shifted into the serial input port, and the value at D will be shifted to Q, so Q is still 0. Now C is Q XOR the LSB, so it is 0 XOR 1, so it is 1. And D is 1 OR Q, which is 1. Now after one more shift, this D goes to Q. The 1 at C goes to the shift register. So the value of C now is 1 XOR Q, which is 0, and value of D is now Q or 1 or 1, which is 1. At the next shift, you get 0 0 1 0, which will give you, and Q will go to 1, which will give you C is equal to 1 and D is equal to 1. Next is 1 0 1 0. D is Q is 1, C will be 1, D will be 1. So next is Sorry, give me a minute. I'll check if there's some mistake that I've made. Alright, here's the explanation for the working of the circuit. If you have a number, say A3, A2, A1, A0, each of the bits is represented by AI, or I belongs to the set 0, 1, 2, 3. And AI can be either a 0 or a 1, it's a binary number. Now, when you want to find the 2's complement, you have to add 1 to A3 complement, A2 complement, A1 complement, A0 complement, or add A3 complement, A2 complement, A1 complement, A1 A0 complement to 0, 0, 0, 0 with carry in equal to 1. Okay. Now for each of the bits, the sum is equal to A complement XOR 0 XOR the carry in. So you are not actually adding, since you're adding 0, 0, 0, 0, you don't have to take that into consideration. A XOR 0 XOR Cin will reduce to A XOR Cin. Now the one property of XOR is that this can be rewritten as A XOR Cin complement. So sum at the stage I is equal to AI XOR Cin complement. So A0 is A1 A0 XOR 1 complement, which is A0 XOR 0. We will make it so that the flip flop contains or stores Cin complement of the previous carry. See, so there is a carry out from a particular stage which will serve as the carry in for the next stage. So initially for S0 the carry in is given from externally, and then once you sum S0, once you find S0, if there is a carry in that stage, so the carry in at stage I will be nothing but AI into the carry in, which is nothing but AI plus the Cin complement whole complement. So Cin instead of writing it as Cin, I'll write it as the carry produced in the stage I minus 1. and the carry in the ith stage that is produced will be equal to ai complement and the carry from the previous stage. So this, for a half adder, sum can be 0 0 0 1 1 0 1 1. The inputs can be 0 0 0 1 1 0 1 1. If you are adding 0 0, the carry is, the sum is 0 1 1 0, which is a XOR b, and the carry is 0 0 0 1, which is ab. Now you are adding 1, you are adding the previous carry to the complement of the number, right? You're complementing and then doing the addition operation. So the sum at ith stage ai complement XOR ci minus 1, which can be again written as a XOR ci minus 1 complement. That's the property of the XOR operation. And the carry for produced in the stage I is ai complement into ci minus 1, which is nothing but ai plus ci minus 1 complement whole complement, which is not, which means that ci complement is a or ci minus 1 complement. Okay, we are using this and this. The flip-flop will store ci minus 1 complement before the ith clock pulse is applied. Since initial carry c minus 1 is equal to 1, c minus 1 complement is equal to 0, so the flip-flop is reset to 0. So initially the flip-flop is reset to 0, then the complement of the previous carry is stored in each stage, and the complement is the output in each stage. And in the ith stage, the complement of the carry is nothing but the sum of the ith bit with the complement of the carry of the previous stage. So you have ci minus 1 here, ci minus 1 complement here, and ai here. So the OR of those is fed as the input, which will come as the output in the next stage. And the sum is nothing but ai XOR ci minus 1 complement. So it's ai XORed with ci minus 1 complement. Suppose you had you wanted to add 1 to the uncomplemented form of the circuit, uncomplemented form of the number. You just wanted to add 1. Then what you could have done is, instead of this, then you would have a sum is equal to ai XOR ci XOR ci minus 1, and ci is equal to ai and ci minus 1. So you would replace with this OR gate with an AND gate. You would keep the XOR gate as it is, and you would store the previous carry in the flip-flop. So you would initially set the carry to 1, and then proceed. Okay. Six point one one. A binary ripple counter uses flip-flops that trigger on the positive edge of the clock. What will be the count if A, the normal outputs of the flip-flops are connected to the clock, and B, the complement outputs of the flip-flops are connected to the clock? So in the first part, if you connect the normal outputs, we get a down counter that counts down from 1111 to 0000 and starts back at 1111. If you connect the negative, if you connect the complement of the outputs of the flip-flops to the clocks, get an up counter that counts up from 0000 to 1111 and starts back at 0000. 6.12, draw the logic diagram of a 4-bit binary ripple countdown counter using A, flip-flops that trigger on the positive edge of the clock and flip-flops that trigger on the negative edge of the clock. If you have positive edge triggered flip-flops, then you give the clock here, then you connect the, if you want to get a down counter, then you connect the normal outputs as we saw in the previous question to the clock pulse, to the clock terminal. And that will give you a down counter. All these are connected to one, their toggle flip-flops. If you want a down counter with negative edge triggered clock pulses, then that means you have a bubble at the clock, so the clock is inverted and the negative edge triggers it. So you simply connect it to the complemented outputs of the T flip flop. Show that a BCD ripple counter can be constructed using a 4-bit binary ripple counter with asynchronous clear and an AND gate that detects the occurrence of a counter 1010. The occurrence of count 1010. A BCD counter goes from 0 to 9. That means that whenever the output wants to go to, it counts, it goes from 0000 up to 1001, and whenever the output wants to go to 1010, immediately the counter should reset to 0000 and start counting from 0000. A binary ripple counter can count from 0 to 15, so it can go from 0000 to 1111, which means that if at whenever we encounter the combination 1010, if you reset the output to 0, it will only count up to 9. Whenever it begins to count to 10, it will automatically be reset to 0. So you have A0, A1, A2, A3. This is the LSB, MSB. You have reset. So reset is active low, that is whenever reset is set to 0, it will whenever the reset input is 0, it will reset the entire circuit to 0000. That is, it will reset the outputs to 0000. So I'm assuming that you start out at 0000. So there is no other combination before 1010 that has a 1 in the 8th place and 1 in the 8th place and a 1 in the 2's place. So all the combinations that have a 1 in the 8 and 1 in 2's place are numbers above 10. So it's 1, 11, 14 and 15. So I'm assuming that the counter starts at 0. If it starts at some combination outside of 10, say, then you'll have to wait for it to count up to 15, and then once it goes back to 000, it will start counting again. And once it reaches 10, the eighths place and the twos place are both 1, and the NAND of those ones will be a 0, which will reset the entire circuit, which will reset the entire counting operation. Problem 6.14. How many flip-flops will be complemented in a 10-bit binary ripple counter to reach the next count after the following counts? So A, it goes from 100110011. To reach the next count, you add 1 to that number. And when you add 1, you will get 1 carried over, 1 carried over. So the number of flip-flops that are complemented will be equal to the number of bits that were complemented. So the first 4 bits have been complemented. So 4 flip-flops will be complemented. Similarly, for part B, you have 1111 000 111. When you add a 1, you will get 0 with 1 carry, 0 with 1 carry, 0 with 1 carry, 1 0 0 1 1 1 1. So again, these 4 bits have to be complemented. So 4 flip-flops will complement their outputs. Part C, 0 0 0 0 0 0 1 1 1 1. And when you add 1, have 0 with 1 carry, 0 with 1 carry, 0 with 1 carry, 0 with 1. The rest are just zeros. Here 5 outputs have changed state, they have flipped. So 5 flip-flops will be complemented. Problem 6.15. A flip-flop has a 3 nanosecond delay from the time the clock edge occurs to the time the output is complemented. What is the maximum delay in a 10-bit binary ripple counter that uses these flip-flops? What is the maximum frequency at which the counter can operate reliably? So the maximum delay that can occur is say when you go from the state 1111 to 0000. In that particular case, first the MSB 1 at the MSB must change to 0. Then that change will trigger a change in the second bit. If you have a number 1111, it's a ripple counter, so the output of the first is fed to the clock of the second. It's a down counter. The complemented output is fed to the clock. So let's say a clock pulse occurred. Initially it is in state 00. is Q1, this is Q0, this is Q1. This is range state 0 0. The first clock pulse occurs. Q0 must change, but it should have changed here itself, should have toggled there itself, but because there's a delay, it will change after some time. So this is the delay, and then again when another clock pulse occurs, it will change like this. So now the complement of this is Q bar, which is initially high. It will fall down, go up, fall down, go up. Now whenever the positive edge in Q0 bar occurs, that will trigger the second flip-flop to change its state. So before that it is at 0. This is Q1, Q0, Q0 bar. Now when it encounters this clock pulse, it should have changed to 1, but there will be a delay, so it will go, and the delay is the same for both flip-flops. And then here also when it has to fall down, it will be delayed. So now assume an input combination, an output combination, say 1 1. So Q0 is at 1. At this clock pulse, it is supposed to fall down, but it will get delayed. Fall here, go up here, fall here, go up here, fall here, and then Q0 complement is this. Now Q1 will treat Q0 as its clock. It was initially 1. It falls down at this point after a delay, then goes up, and so on. So now this 1 1 was supposed to go to 0 0. It was supposed to go back to 0 0, but in this portion it is at this portion it is 1 1 still. This portion it's 1 0. This portion it drops to 0 0. So it was supposed to go to 0 at this point itself. The total delay causes 2 times the delay of each flip-flop. If this occurs for n number of flip-flops, if there are n bits in the output, then the delay maximum that you could have n times delay of one flip-flop, where n is equal to number of output bits is equal to number of flip-flops. It is better to write it as number of flip-flops itself. So it is in this case 10 flip-flops. It's a 10-bit binary counters, and each one has 3 nanosecond delay, so the total delay is 30 nanoseconds. So that's the maximum delay that you could have. Now if your clock okay, coming to the second part of the question, what is the maximum frequency at which the counter can operate reliably? So the frequency at which it operates should have a time period that is greater than 30 nanoseconds. So it can, the minimum maximum frequency that it can operate at is nothing but 1 over the maximum delay, which is 1 over 30 nanoseconds, 1000 over 30 megahertz, 33.3 megahertz. So if you don't have a frequency, if you don't have the time period at least 30 nanoseconds, then the time period is smaller than that, then the change in the output would not have even fully occurred. So from 1111 at 15 nanoseconds, you might not even have changed your output to 00000. So if you take the output at that time instant, if you have some circuitry that is taking the output and measuring it and using it before the entire 30 seconds is up, then it might use the wrong output. It might use the wrong count. So the entire working of any circuit you use, which depends on the counter, is compromised. So before you, once you change, once you once you sample the output at the counter, you'll have to wait at least 30 nanoseconds before the next count occurs. I'm not sure if that is clear to you. I can't remember of an application right now, but if you come across a circuit that you're trying to design a circuit that depends on a counter, on the counter output, then you might realize why this is important. We'll skip 6.16. We'll skip 6.17 also. 6. We'll skip 6.18, 19, 20. We'll solve 6.23. Design a timing circuit that provides an output signal that stays on for exactly 12 clock cycles. A start signal sends the output to the state 1, and after 12 clock cycles the signal returns to the 0 state. So initially the start signal 1, the start signal is set to 1. So there is a signal that will send the output to the 1 state using the 1 output. To do this, we can use a ripple counter that counts exactly 12 clock cycles. So after 12 clock cycles, it should stop counting, and the output should go to 0, and it should stay the same. Sorry, I zoned out a bit. There is not much time left. There's just 5 minutes left, so I'll skip this. I'll go to one numerical question, do that, and end this session. 6.26. A digital system has a clock generator that produces a frequent pulses at a frequency of 80 megahertz. If clock is 80 megahertz. Design a circuit that provides t is equal to 50 nanosecond pulses. So t is equal to 50 nanoseconds means that frequency needed is 1 over t, which is 1 over 50 into 10 power 9, which is 1000 over 50 megahertz, which is 20 megahertz, which is the clock frequency divided by 4, clock, clock frequency by 2 square. So we can use a ripple counter with we can use a 2-bit ripple counter with 2 flip-flops. The first ripple counter will divide the frequency by half because it is only positive or negative edge triggered. For example, if you have a flip-flop, you're using a toggle flip-flop and you give your clock here, and this is your output Q. Let's call this Q1. If this is the clock signal which has a time period T clock, then the output Q1, suppose it's initially at 0, it will become high at the positive edge, go low at the next positive edge, become high at the third positive edge, and so on. So the time period of the first output T1 is 2 times T clock, which implies F1 is F clock by 2 because time period is inverse of clock frequency. If you had another flip-flop, and the output of this was connected to Q1, this was also a toggle flip-flop, the output Q2 would now get triggered at the positive edge of Q1, so it will change here, next positive edge would be there. So this is T2 by 2, T2 is much larger, that's only half of the wave, so T2 by 2 is equal to T1, T2 is 2T1, which is equal to 4 times the clock pulse. So the frequency F2 is F clock pulse by 4. So use the 80 megahertz clock here, you will get a 20 megahertz clock pulse. Alright, that's it for chapter 6. In the final session, we'll cover problems from chapter 7 and end the lecture series.